Happy Math Hour, our weekly interactive math reviews for Math 1314 and 1324, which are presented by Yvette Chuca, Albert Isasi, and Ruben Carizales. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who have missed out on today's event will be able to come back and watch it. Please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we will be sharing. If you are here for the Math 1324, we will be posting the room link on the chat so that you may connect to the Math 1324. We also will be sending individual messages to everyone who so we can gather your student ID number to sign you in. And now, without further ado, I will pass it on to our presenters so that they may begin.
Hello, everyone. Welcome to Friday Happy Math Hour. So as they said, they're going to put a link for the 1324. And if you're in 1314, we're going to continue with our Friday Happy Math Hour. If you are taking a Summer 2, 1314, this session today is going to start in Chapter 3. However, throughout our session, they're going to be posting some YouTube links. You can always go into the YouTube and view the first few sections of 1314, especially if you're in the Summer 2, 1314. So we're going to continue with exponential and logarithmic functions. And so as we've been looking at every semester, we have exponential functions. We've looked at linear functions, quadratic functions, and so on. And so an exponential function is a new type of function that we're going to look at. And as you can see here, the function is set up as f of x equals a to the power of x. And so the a is what we call the base. And then notice that the exponent is going to be a variable. Okay. And so we're going to look at this a little bit closer. But let's just look at a situation here so that we can get an idea of what an exponential function is and how it grows. So suppose that I gave you an option to receive a penny on the first day of class, and then the next class day, I would give you 2 pennies. And then on the next day, I would give you 4 pennies and then 8 pennies and so on. Okay. Or you would have an option of getting $1 million on that first day. Which one would you take? Okay. So some of us would take the $1 million. You know, it's not bad having $1 million right away, right? Some of you might be like, oh, I don't want any pennies. Why would I want a few pennies? Like, what am I going to do with 8 pennies? I don't think I can buy not even a candy anymore with 8 pennies. But let's see what happens. Okay. So here's a table. So on day 1, I give you 1 penny. On day 2, you get 2 pennies. On day 3, you get 4 pennies. And then on day 4, you get 8 pennies and so on. Okay. So how many pennies would we have on the 31st day? So to get that, that would be 2 to the 30th power. So if we were to calculate this on our calculator, it would look something like this. But remember, this number here is in pennies, right? So we have 1 billion and pennies. So to find out how much it is in dollars, we would just move our decimal over 2 places. And so if you chose this option, you would end up with $10,737,418 dollars as opposed of the 1 million that you could have gotten from the beginning. So as you can see, even though we're talking about pennies here, when it's an exponential function, it grows very quick. Okay. So in this problem, the equation that we could use is f of x equals 2 raised to the power of x. And so if we were to graph it, which we're going to be doing here in a second, you would see that the graph is going to look something like this picture here. But in general, if you have an exponential function, again, the a is our base, and then we have our variable x as an exponent. So if we look at this graph, this point here, 0, 1 is our y-intercept. And that's going to be the case for any problem that is going to look like this, such that in front of a you have a 1. Okay. The domain is from negative infinity to positive infinity because we're using all these x values to be able to draw this graph. And then the range is from 0 to infinity. Again, the reason is because we're only using the values for the y-axis from the point 0 and going up. And then the y-intercept is 0, 1. And it's this function, we say that it's increasing. And then this is going to have a horizontal asymptote at the x-axis. And so the horizontal asymptote, we looked at those in 2.6. And again, the graph is continuous. Now, what happens if we have a function that looks in this direction, right? So the previous one is increasing, but what if it's decreasing? Okay, if it's decreasing, then notice here that if we have the same equation, y equals a to the x, whenever a is between 0 and 1. So if your a is a fraction, like this one here, then your graph is going to be decreasing, okay? If a is a whole number, like this one here, the number 2, but you have a negative exponent, then your graph is still going to be decreasing. The domain remains the same, the range is the same, your y-intercept is the same. Instead, it's decreasing instead of increasing, and then it's continuous. Okay, so let's look at f of x equals 3 to the x, and then we're going to go ahead and graph it. So in this problem, notice that my letter or my number a, the a here is 3. And so 3 is not a fraction. And then our exponent is positive. So when we graph this, our equation is going to be increasing. Okay, so let's see if that happens. So I have a table of values here. So in chapter 1, we learned how to plot points, right? So if x is negative 2, we're going to replace x with negative 2. So we get 3 to the negative 2. Whenever we have a negative as an exponent, we can rewrite it as a fraction here. So we get 1 divided by 3 squared, and then 3 squared is going to be 9th. So we get 1/9. If I plug in negative 1, we get 3 to the negative 1. So that becomes 1 divided by 3 to the first power, which is 1/3. And then for 0, if I input it here, anything to the 0 power is always going to be 1. And then the 1, 3 to the first power is going to be 3. So if I plot these order pairs, this is what they look like here. And if I draw the graph, then my graph is going to look like this. And notice that the graph is getting closer and closer to the x-axis, but it's never going to cross it. And that's what it means to have an asymptote. Okay. Now in chapter 1, we also learned that we can use a vertical line test to determine if a function is or an equation is a function. And so in this section, we can use a horizontal line test to determine if a function is one-to-one and has an inverse. And so if we were to look at this exponential function, and if I draw a horizontal line, notice that it only crosses in one spot on the graph, and therefore it tells me that there's this function is going to have an inverse, and that it's one-to-one. Well, the inverse of exponential functions are logarithmic functions, which in a little bit we'll go into to learn more about those logarithmic functions. For now, one of the most important properties in this whole chapter is called the one-to-one property. And the one-to-one property allows us to be able to solve for a variable. So if you remember, let me just draw something really quick. This whole semester, we've been looking at equations that look like this. And notice that the x is actually not an exponent, right? And so for us to solve this, we were taking the square root, and we would get our answer. But now in this section, the thing that is different is that the exponent is a variable. Okay, since the x is an exponent, then we can't do the same idea that we did before by taking the square root. And so this is where we're going to have to use different properties. And one of those properties is the one-to-one property. Okay, and so the one-to-one property says that if you have two exponential functions, and notice that they both have the same base, they both have a, then we can just set the exponents equal to each other, and that's how we're going to bring the variables down so that we can solve for them. So for example, if we have 10 raised to the 2 minus 4x is equal to 10 raised to 6x minus 1. Can we use the one-to-one property? So the first thing you want to check if you can or can't use the one-to-one property is to ask yourself, is the base, that's the number that has the exponent, are they the same? And as we can see here, they are the same. And we don't have anything else with them, okay? So for example, if you have 2 to the x is equal to 2 to the x plus 3, and then you have a number, let's say plus 5, then for this equation here, or this equation, we cannot use the one-to-one property because it has this extra 5. So one of the conditions is that they have the same base and that there's no extra operations with it, okay? So now that we can see that we can use the one-to-one property, then let's go ahead and apply it. So since the bases are the same, the property tells us that we can set the exponents. So this is my exponent. So I'm going to have 2 minus 4x. I can set it equal to the other exponent, which is 6x minus 1. Now we can solve for x. Okay, so let's solve for x. So I'm going to subtract this 2 on both sides. I'm going to subtract this 2 on both sides. And I'm going to subtract the 6x on both sides. So 2 minus 2 is 0. Negative 4x minus 6x is negative 10x. My 6x and negative 6x will become 0. And negative 1 minus 2 is negative 3. Divided by negative 10. So we get 3/10. Okay, so that's going to be our answer for that equation. So let's look at this equation. Solve the given equation for x. So my first question is, can we use the one-to-one property? So I'll give you a few seconds to think about it, if you can or can't, and then I'll give you the answer right now. But what is that one first condition? That first condition is to check the bases, right? So I have a 4 and a 64. So the question you want to ask yourself is, are they the same? So the answer is no, they're not the same. So the second question is, can we make them to be the same? And so that's what you want to look for. Can you change 4 to be a 64, or can you change 64 to become a 4? And so that's what we'll do on our next slide. Okay, so we have the same base. So here the 64, we can write it as 4 cubed, because 4 times 4 times 4, 4 times 4 is 16, times another 4 will give you 64. So now they're the same. So we can apply the one-to-one property, and that tells me that I can set my exponents equal to each other. So x plus 1 is equal to 3. I'm going to subtract 1, and I get x is equal to 4. Or we're subtracting 1, so we get that x is equal to 2. Okay, so that would be our answer for x. Let's try a couple more. Okay, so here we have 5x minus 3 is equal to 1 divided by 125. And so here we can see that these numbers are not the same. We have a 5 and 1 over 125. And some of us might think, well, I know 125 is the same as 5 cubed, right? Because 5 times 5 is 25, times another 5 is going to be 125. But if I have let me get my pen out again. If I have 5x minus 3 is equal to 1 divided by 5 cubed, then this is not the same as this yet. Okay, so what we can do is we can rewrite 1 divided by 5 cubed. If I want to take this 5 to the numerator, I can do so, but I'll have to change the sign of my exponent. And so that's how I got 5 to the negative 3. Now that they are the same, then we can go ahead and set the exponents equal to each other. So we have x minus 3 is equal to negative 3. I'm going to add 3 on both sides. And so if I add 3, negative 3 plus 3 will be 0. And if you want to check your work, you can always take your answer, plug it in for x here to see if we get 1 divided by 125. Okay, so in addition to these exponential functions, we have the number e. So the number e is an irrational number. It's kind of like the number pi. Some of you are familiar with the number pi. It's 3.14 and it goes on forever. And so for the number e, that's approximately 2.718 and so on. And we call this number the natural base. Okay. And so if we look at the function f of x equals e to the x, our base is going to be e. And again, this is your natural exponential. Okay, so the way it looks, since e is 2.7 and so on, then that means that it's an increasing number. I mean, an increasing function. That's why the graph looks like the other one we had. And then let's go ahead and try some examples. So here it says solve the given equation. So we have e x raised to the x squared minus 3 is equal to e to the 2x. So always, my recommendation is to always ask yourself if you can use the one-to-one property, because if you can, then that usually will save you time. So my question here would be, can I use the exponential, I mean the one-to-one property? And the answer is yes, because they both have the same base. So now that they both have the same base, then we can set the exponents equal to each other. X squared minus 3 equals 2 to the x. Notice that this is quadratic. So in chapter 2, we covered quadratics, or you will be covering quadratics. And so if I subtract 2x to the left side, then we need everything to be on one side. So I'm going to have x squared minus 2x minus 3 is equal to 0. Since this is quadratic, then we have options to solving it. We can try to factor, or we can use the quadratic formula. And so for this example, I'm going to go ahead and factor it. So x squared I can get from x times x, and then negative 3 I can get from negative 3 times 1. And if I take negative 3x and 1x, that's going to give me a negative 2x. So that works out. Set the factors equal to 0, so we get x equals 3 and x equals negative 1. So those are my solutions for this problem. Another thing that we have is something called the compound interest formula. And this is used it's used by different types of banks, for example, like on credit cards, on just different types of things that we are used for. Well, you don't want to use it to retire because it's not going to provide the money that you need. There's other tools that you can use for that. But the compound interest formula is given by A is equal to P parentheses 1 plus R divided by N raised to the NT. A is your future value. That is how much you want to have in the future. P is your principal. That's how much you're going to invest. And then R is your rate, your interest rate. And then N is going to be how it's compounded. So compounded can be compounded by month, compounded by year, compounded weekly, compounded yearly, semi-annually, and so on. And then T is going to be your time. Okay, so here's some examples. So if it's daily, we would use 365. If it's monthly, we would use 12. If it's quarterly, we would use 4, and so on. Okay, so here we have an example. Find the amount to which 1500 will grow if deposited in a bank at 5.75% interest compounded quarterly for 5 years. Okay, so let's go ahead and see what we have. So here I have 1500. That is how much money you're investing or what you're beginning with. So that's going to be your P. Your rate is 5.75%. So I'm going to move the decimal to the left 2 places and I get 0.0575. It says compounded quarterly, so that's going to be 4 for quarterly. So that's your N. And then we're going to do this for 5 years, so that's going to be T equals 5. And then I'm going to plug in into the formula. So we get 1500 parentheses 1 plus 0.0575 divided by 4, 5 times 4. So my recommendation is when you're doing these problems, you don't want to round till the very end. So when you enter 0.0575, then I would divide it by 4 plus 1, and then I'm going to raise it to the 20th power. And whatever you see on your calculator screen, I would use the whole number, and I would just press times 1500. And then at the end, you do want to round to 2 decimals since you're talking about money. Okay, so if you notice, it didn't grow that much, right? About $495. And that's why I said earlier, you don't want to use this vehicle for retirement because then in 5 years, you only got $400. So there's other vehicles you can use like annuities and so on. So let's have another example. So a couple just had a baby, and how much should they invest now at 5.8% compounded daily in order to have 35,000 for the child's education 18 years from now? And so assume 365 days per year. And that's important because some banks will say that there's 360 days instead of 365. And so you just have to see what year, if they're going by 365 or 360. So here, what is P is what we want to know is how much do we have to invest. So we don't know what P is. However, A is how much you want to have at the end, which is 35,000. Your rate is 0.0575, and we're going to compound it every day, so 365, and we're going to do this for 18 years, okay? So we plug it in. We have 35,000 for A, and we have all the information here. 0.058 divided by 365 is this decimal here, and then I'm going to add it to 1. And so I get 1.0, so I get 1.0 so on. And then we're going to raise it to the power of 6,570. And I get 2.84 so on. And now I'm going to divide by that number so that I can solve for P. And so the couple should invest $12,322 to get back 35,000. Okay. So that was 2 examples for compounding interest. We also have something called continuous compounding, which is A equals PE raised to the RT. And continuous compounding is when you're just continuously compounding, right? Or the last one we saw was 365 days. Well, what if you wanted to do it every minute, every second, or whatever it is? So instead of doing that, we just use the continuous compounding formula. So those were all examples from 3.1. Now we're going to look at 3.2. So logarithmic functions. These are functions that are the inverse of exponential functions. And so the way they look, if you look at this graph, the black where I'm pointing, this is your exponential function. And then the log function is the one that I'm pointing here on the bottom of the screen. That's your logarithmic. And so these are inverses of each other, and we can tell by this dotted line that tells us that they have an inverse of each other. So the domain of the logarithmic function is a set of all positive real numbers, and the range of the logarithmic function is a set of all real numbers. So here we're using, let me go to the next page here. So if we look at common logs and natural logs, we have the common log is log x. If you see log x, that is the same as log with the base 10. So the little numbers that you see here, those are going to be your base, okay? So for example, earlier I mentioned that, let me get the pen. We had something like this. So this was your base. In the logarithmic functions, these numbers here, the little numbers, that's your base. But when it's a common log, you're going to see it without that number. So if you see log without the little number here, then that means that it's base 10. And then if you see the word natural log, that means that it has a base of e, okay? And one of the common mistakes that I get from students is when you're doing your work on WebAssign, they enter an I for this, but this is not an I, it's an LN. Okay, so one of the things that we want to do is we want to write logarithmic functions and convert them to exponential functions, or we want to go from exponential to logarithmic. So we want to go from one form to the other. So this function here is a log function because it has the word log. And what we want to do is we want to write what its equivalency is in the exponential form. And so notice here that the base is 4. And so I'm going to write the base for my exponential function as 4. So this 4 here is going to be our base right here. And then this entire log is equal to x. And so x is always going to be your exponent. Okay, and then we have the 16. So the way I like to say it is that the log is always equal to the exponent, and then that will help us to rewrite it. Okay, so let me give you another example here. The number 2 is going to go from exponential to logarithmic. Okay, so if we were to change it to a log, then I'm going to write the word log first. And then your base, what is your base? 5. So we're going to have a little number here, 5. That's going to be my base. And then I know that I have to have something in here, and this is going to be equal to, oops, that's going to be equal to something else. Okay. So what is the log equal to? The log is always equal to the exponent. So my exponent is 3. So I'm going to put that one over here because that's what the log is going to be equal to. And then my number on this side is going to be in the parentheses. So we have log 5 of 125 is equal to 3. Okay, let's try this one. So now this one is a base, log with a base of b. 27 is equal to 3. And since it's in log form, we want to change it to exponential. So the first thing you want to ask yourself is, what is your base? Your base is the letter b. Okay. And then we know, again, so I'm going to be repetitive here, but the log is always equal to the exponent. So in this example, the log is equal to 3. So that makes 3 my exponent. And then we have our other number, 27. Okay, so that's our answer. So let's try this one. So we have the square root of 81 is equal to 9. So when we first look at this, it looks like we don't even have any exponents and we don't have a log. So whenever you see square roots, you want to rewrite them. The square root is the same as 81 to the raised to the power of a half, and that's equal to 9. So in this chapter, anytime you see a square root, you're gonna rewrite it as an exponent of a half. If we had 81 of the cube root, then that's just gonna be 81 raised to the 1/3 power. Okay. If we had to the fourth root, then that would be 81 to the 1/4 power. So you always want to go ahead and rewrite it as a fraction, as an exponent. Okay, so now that we have 81 raised to the power of 1/2, then we can go ahead and change it to a log. So I'm going to have the word log. Let me see, get my pen out again. So we're going to have the word log. What is our base? Our base is 81. And again, I have that one statement, right? What is the log equal to? The log is always equal to the exponent. And so our exponent is a half, so that's going to go on this side. And then we have the other number, which is 9. Okay, so that's going to be our answer. And then we have the other number, which is 9. Okay, so that's going to be our answer. And so notice here I rewrote it, and then we just finish up the answer. So in this section, we're also going to look at several properties because these properties will eventually help us to solve for x. So these properties are listed here. If you notice, log a of 1 is equal to 0 because if we change this to exponential, we would have a raised to the 0, which is equal to 1. If your base is a and you have this number a, if these are the same, then that's always equal to 1. If you have the bases are the same here, raised to an exponent, then the answer is that exponent. And then for logs, we also have the one-to-one property. And the one-to-one property tells us that if you have a log with the same base, so in this case a, then we can set x equals to y. So we'll get to practice with some of these. So it says use the properties to solve. So we have log 3 of 127. So what we can do here is there's two ways to solve for this. One way is to convert this information here to exponential. And then the second way is to use the properties. Okay, so I'm going to first convert it to exponential form. So my base is 3. So I'm going to write 3. What is this log equal to? It's equal to the question mark. So I'm going to have 3 to the question mark is equal to 1 divided by 27. Can I use the one-to-one property here? Not the way it's written, but 27 is the same as 3 times 3 times 3. So we can rewrite it as 3 to the negative third. And now since they have the same base, I can set the exponents equal to each other. So question mark is equal to negative 3. And so this log, my answer is negative 3. So that's one way to do it is if you see something written as a log, you can always change it to exponential form. Now, if we use the properties, then here we could use, oops, let me go back. I went too quick. So I could rewrite 1 divided by 27 as 1 divided by 3 cubed. And then I can move the 3 cube up by making it negative. So now I have log 3 of 3 raised to the negative 3. And notice that my base and my base here are the same. And so which property could we use here? So we have a base and then a base with something raised to the x power. And so we can use this property. So my answer is just going to be that exponent, which is negative 3. Okay, so since these two bases are the same, your answer is going to be the exponent of negative 3. Okay, so now if we go to the next problem, we have log pi of pi to the 5th power. So again, your base is pi, and the base here is pi. So again, property number 3 is going to be the one that we can use. And so that tells me that if these two are the same, then my answer is going to be the exponent, which is 5. And here I have log of 7.5 is equal to 1. I'm sorry, let me say that again. So log of 7.5 of 1. And so if we look at our properties, we have property number 1. If you have a 1 here, then your answer is just going to be 0. Okay. Here we have log 90 of 90. So if these are the same, then we're looking at property number 2. We have A and A. So our answer would just be 1. But again, if you don't remember the properties, then it's okay. We would just, if you don't remember all these properties, that's okay. Then we could just change them to exponential forms. Okay. So which property does this fourth one look like? So we have 3 raised to the log of 3, 8. So you have a base of 3 and the log has a base of 3. And so that's going to look like property number 3 again. And so according to property 3, our answer is going to be 8. Okay. Now let's go ahead and solve equations because that's really what the important thing is here. So we have log b of 1000 is equal to 3. And so if you want to solve for x, then, or in this case, you want to solve for b, notice that b is kind of trapped in here with this log. So in order for us to be able to solve for it, we can change it to exponential form. Okay, so here I can change this to exponential form. So I would get b cubed is equal to 1000. Now I can take the cube root of 1000, right? So here we're going to have, or you can write the 10 cube is fine too. And so b would be 10. So you can take the cube root or what power, what would b have to be so that it looks like 10 cube, it would have to be 10. Okay, let's try this one. Log 6 x is equal to 5. So if we change it to exponential form, my base is 6. The log is equal to the exponent, so that makes 5 the exponent is equal to x. And then we can simplify. So 6 to the 5th power is 7,776. Okay, so for these two examples, we converted from log to exponential form to get our answer out. So throughout the whole chapter, we can use these properties. So we already looked at numbers 1 through 4. 5, 6, 7, 8, I believe will be in the next properties. Okay, so here it says solve this equation. So notice here that the log has a base of 5. And on this side, we have log base of 5. So since they have the same base, then we can set x plus 1. So we're using the 1-to-1 property. So we can set x plus 1 is equal to 9. Now we can only do this again because they have the same base. So now we can solve for x. So I'm going to subtract 1 and we get x is equal to 8. So in logarithmic functions, you always have to check your answer because if you remember, let me sketch the graph really quick. On one of the first slides, the graph looks something like this. Okay, and so what this tells us is that the domain for logarithmic functions is from 0 to infinity. In other words, we're only using the x values here. So whatever is going to be in this parentheses has to be positive. Okay, so whenever you solve for your x, you have to make sure that that's going to be the case. And so if our answer is 8, if I plug it in here, I would get 8 plus 1 is 9, and 9 is positive, so that's okay. So x equals 8 is a solution. Okay, so let's try another example. Here we have log 17 is equal to log x squared plus 8. So the base for this log, we don't see the little number. So if you don't see a little number, just remember that that means that you're in base 10. And so you have something like this. So this is the same as log 10 of 17 is equal to log 10 of x squared plus 8. Okay, so the important thing is that they have the same base. And since they have the same base, then we can set the equation up as 17 equals to x squared plus 8. Okay, so 17 equals to x squared plus 8. So I'm going to subtract 8 on both sides, or subtract 17 on both sides, that's fine. So we get 8 minus 17 is equal to negative 9. I'm going to add 9 on both sides. So we get x squared is equal to 9. Take the square root. So we get plus or minus 9. So that becomes x is plus or minus 3. So we have two possible solutions. And so x equals 3 and x equals negative 3. In order to find out what if they are solutions, we have to plug them in. So if we have a positive 3 here, we would get 3 squared is 9 plus 8 is 17. So that's okay. If we have a negative 3 squared is going to be 9 plus 8 is also going to be positive. And so they are both solutions, okay? Again, the reason they're both solutions is because the resulting number is positive. So here's another one. Natural log of x squared minus 3x is equal to natural log of 18. Remember that the natural log is simply, this is also the same as log e of x squared minus 3x and equals log e of 18. So again, they both have the base e. That means we can set up an equation using the one-to-one property, which is going to be x squared minus 3x is equal to 18. Since this is quadratic, that means I have to put everything on the same side. So I'm going to subtract 18 and I get x squared minus 3x minus 18 equals 0. And now I can try to factor this or use a quadratic formula. It is factorable. So now I can set the two factors equal to 0. So one possible solution is x equals 6 and the other one is x equals negative 3. And so if I plug in 6, let me see if I have that on the other slide. I don't. Okay. So let's check. So if I plug in 6 here, I get 36. And if I plug in 6 here, I get negative 18. So 36 minus 18 is going to be positive, so that's okay. So that's a solution. And then negative 3, I'm going to have negative 3 squared is 9. And then here I'm going to have positive negative 3 times negative 3, which is positive 9, plus a 9 is 18, so that's going to be okay as well. So the solution works for both of them. Okay, one more. So x plus 6, log 4x plus 6, plus log 4x minus 6 equals 3. So here we might be thinking, well, this is a 4 and this is a 4, so maybe I can use the one-to-one property. But the problem with it is that it has an extra 3 over here. And even if I took my log to the left side, I'm still going to have to deal with that 3. So we're not going to be able to use the one-to-one property. Okay. So in the next sections, we would be able to use different sections or different properties. So in order to do this problem, we're going to have to combine, let me just circle. We're going to combine, excuse me, we're going to combine these two. And then once we combine them, then we'll be able to change it to exponential functions. So really, we're going to be using this property here, number 5. And so for that one, I guess we'll wait for next week, or I guess we have some time. So let me see. So we're going to have log. I haven't covered the property yet, but just so you can get an idea of what it looks like. So basically, the property says that if you have, if you're multiplying 2 of these here, we can separate with addition. But if they're written as addition, you can combine them as one log. You can condense them and into multiplication. And so if I do that, we have log 4, and then we're gonna go ahead and multiply that. So x plus 6 times x minus 6, and then that's equal to 3. Okay, and so that's what the property allows me to do, is to take 2 logarithms and condense them to just one logarithm. So now I would multiply, so x times x, let me write here log 4, x times x is x squared, x times negative 6 is negative 6x, 6 times x is 6x, and 6 times negative 6 is negative 36, and this is still equal to 3. Combine your like terms. So we have log 4 of x squared. The x's here cancel. Minus 36 is equal to 3. Okay, so now we have one log. And so in order to solve for this, we're going to go ahead and change it to exponential form. So if we change it to exponential form, my base is 4, so I'm going to write it up here. Oops. So my base is 4. That's my base. And then the log is equal to the exponent. So this log is equal to, that's my base. And then the log is equal to the exponent. So this log is equal to 3. So that means that 3 is my exponent. And then we have the rest of the stuff. That's equal to x squared minus 36. Okay. So 4 cubed is 4 times 4 times 4. So that's 64. So we get 64 is equal to x squared minus 36. We're going to add 36. So we get x squared is equal to 100. And then take the square root of 100. So square root. So x is equal to plus or minus 10. Okay. So the last thing you want to do is ask yourself, because those are just possible solutions, right? X is 10 and x is negative 1. So to be sure that they are solutions, we need to make sure that if we plug those numbers in here, we result with a positive number there. So if I have a 10 and I plug it in for x, I get 10 plus 6 is 16, and 16 is positive, so that's okay. And if I plug in the 10 here, 10 minus 6 will give me a 4, and that's okay. But now let's look at the negative 10. So for negative 10, if I plug in negative 10 here, negative 10 plus 6 gives me a negative 4. So I cannot take the log of a negative number. So that means that the only solution is 10. So your answer would only be 10 and not negative 10. Okay. So if you have any questions, please let me know. This was examples from 3.1, 3.2, and a little bit of 3.3. Next week we'll finish up with chapter 3, and then we'll go from there. If you just started 1314 for summer 2, again, they put the previous links to the YouTube channel, in the YouTube channel, you can find the videos for all of Chapter 1 and Chapter 2. And so those would be helpful for you. And if you're in a 10-week class, then you can also, go back and look at those videos. Now, the other thing I wanted to say before I pass it over is if you want a copy of this presentation, then here where I'm pointing with my mouse, right above, you should see a box with an arrow pointing down. If you click on that, it's going to let you download the entire presentation. So I'll pass it over to our awesome people. I think there might be muted.
Thank you, everybody, for joining us today for our Happy Math Hour session. We hope that you will join us next Friday, July 19th, for Happy Math Hour again. Math 1314 will cover exponential and log functions. And Math 1324 will cover the Exam 2 review. We'll also have the 1 o'clock session next week with the STEM Forte with Dr. Jennifer Jameson. If you have any questions, please let us know. The tutors are available in Blackboard. Feel free to join us at any time, Monday through Friday in person, 8 to 5 p.m., or online from 12 p.m. to 9 p.m., 7 days a week. We're glad you were all able to make it today. If you don't have any questions, have a wonderful weekend, and we hope to see you next week. Thank you, Ms. Chuka, for your awesome presentation today.